done. We can go get ready for Santa Claus. All right, so 8.1, so chapter 8 is going to be dealing with systems of equations. 8.1 is going to be dealing with linear systems. 8.4 is going to be dealing with nonlinear systems. What is a system of equations? It's just two or more equations for which a common solution is sought. So what does that mean? So I have a system right here, and I've graphed it as well. There we go. And it is the two lines, negative 2x plus y is negative 5, and 4x minus 3y equals 9. Now, typically, if you have one of these equations all by itself, you can find a solution to it by plugging in some number for x and solving for y, and then that gives you an ordered pair that satisfies the line. In this case, I have two lines, and what I want to know is, are there any points that land on both of these lines, right? So how do I do that? Well, I want to know is 0 to, so in this one, I'm just being asked directly, is 0 to a solution to that system? Well, the way I check it is I plug in 0 to both lines, and both of them need to come back with something true. All right, so let's try it for the first. So 0 to, is this a solution? All right, well, if it is, then when I plug in negative 2x plus y is 2, equals negative 5. So what I should get back is a true statement here. Do I 0 times negative 2 is 0. 0 plus 2 is 2, and 2 is not equal to negative 5. What that means is that point does not fall on the line negative 2x plus y is equal to negative 5, and I can stop there. Okay, I don't have to keep going. I don't have to also check with the other equation, because the only points I'm interested in are the ones that are solutions to both of the equations in the system. So next, how about negative 1, negative 7? Yeah, you could also look at the graph. It's in there too. So again, let's start with the first equation, negative 2x plus y equals negative 5. Negative 2 times negative 1 is positive 2 minus 7 is equal to negative 5, so negative 5 equals negative 5. Okay, that's half of it. Now I need the other equation. No problem, Andrew. No problem. So let's scoot this over just a little bit. And let's grab that other equation and check if negative 1, negative 7 works for it. So the other equation is 4 times x minus 3 times y is equal to 9. 4 times negative 1 is negative 4. 3 times negative 7 is negative 21, so this is minus negative 21. Minus negative becomes plus. Negative 4 plus 21 is 17. Does 17 equal 9? Nope. So 0, 2 is not a solution. Negative 1, negative 7 is not a solution. But it worked for one, but not the other. So no, it's not a solution to the system. How about 3, 1? You can look at the graph. You know how this is going to go already, right? Negative 2 times 3 plus 1 is equal to negative 5. Negative 6 plus 1. Negative 5 is equal to negative 5. Again, all I'm doing is taking the two coordinates from the point they're asking if is it a solution, and I'm plugging it into the two equations from the system. So the other is 4x minus 3y equals 9. 4 times 3 is 12. 3 minus 1 is 3. 9 equals 9. And so the answer is yes. What does that look like graphically? Graphically, it looks like the place where the lines intersect. Okay? And is that 3, 1? You bet it is. That's the point. All right. Now, I did want to make a note here to just remind you that when I get to systems of equations, a solution of equations is always an ordered pair or triplet. If you have 3 variables, it'd be an ordered triplet, and you can just keep working your way up. But it's always going to be not just a single value, not just x or y. All right, so answers are always ordered pairs for systems of equations, because I can plug in the same x to both equations, end up with different y's, and then that means I don't have a solution. All right, so we have seen 2 failures, 1 success. That's expected. So next we have, this looks a bit different, or the equations are the same, or the graphs are the same. I've got the equations out to the left. What we saw on the first line is we saw 2 linear equations that are that do intersect. So that means they have at least 1 solution. So let me get you the vocabulary for this section. Linear systems are, or let me just say systems of equations. Systems of equations are, can be classed as, and the first is consistent or inconsistent, and then the other is dependent or independent. So what does that mean? Let me just make this one sentence. That'll make a whole lot more sense. So a system is either consistent or inconsistent, dependent or independent. Consistent means the system has at least 1 solution. So inconsistent means the system has no solutions. The at least 1 solution is going to be important, so keep an eye on that. A system is dependent if the equations in the system are unique. In other words, they don't repeat. Sorry, if it's independent. And then the system is called dependent if the system's equations in the system are the same, right? And you're probably wondering, how could I do that? How could I possibly get a system of equations and it just have 2 of the same lines? Okay, well, I'll show you an example on the next page, or the page after that. So consistent, inconsistent, dependent, independent. All right, so next we have these 2 lines. Take a look at them, and yes, we have a small window, but I do know something about how these 2 systems, these 2 lines are related, because they have the same slope, right? They are falling from left to right at the same rate. So what does that mean? All right, well, if they both fall at the exact same rate, they will be parallel to each other forever. Okay, and since they're parallel forever, they never intersect. Remember, a solution to a system of equations is the point where they intersect. If they never intersect, then this system is inconsistent because it has no solution. Now, is it dependent or independent? And this one is independent. because the two equations are unique. Even though they share the exact same slope, they are independent. All right, so if you end up with two parallel lines, they will never intersect. If two lines never intersect and they make up a system, then there's no solution to that system. All right, the other equation or the other system we have is this one. Why does it look so different, or what's going on here? Well, the first thing you probably noticed was there's only one line, right? Well, it turns out it's not just one line. Take a look at the second equation in the system, and you're going to see me do this a lot. I'm going to label these as equation 1 and equation 2. Equation 2, 3x minus 1 over 3, I could rewrite that as 3x divided by 3 minus 1 divided by 3. And then 3 divided by 3 is 1. And look at that. Ooh. I'm not gonna make a mess of this like I did last class. And there we are. Now take a look at the equation. Once I simplified equation 2, what happened? It's the exact same equation as equation 1. So in this case, we have the same line twice. So the system is, this is the dependent, because that's the same line. But then is it consistent or inconsistent? Well, remember, a system of equations has solutions wherever the equations in the system overlap, or if I graph it, where they intersect. This is the same line, so that line is directly on top of the other line. Where do the same line intersect with itself? Everywhere. So that means this is a consistent. Is consistent because there are infinite solutions, and the solutions are every single point on the line, right? Okay. Now, writing a system, writing the infinite, or writing no solution and writing a single solution is fine. How do you write an infinite solution? So how do you write this? So the solution for this, remember we said it's an ordered pair? Well, it is. It's x, comma, and then for the y, what you end up doing is you take either equation 1 or equation 2 and solve for y. Well, they've already done that for us right here, right? Y is equal to x minus 1/3. So xy, this is what your solution should look like, becomes x, comma, x minus 1/3. All right. Why does it need that? Because I said there's infinite solutions, but it's not every single ordered pair in the world that is a solution. It's only the ordered pairs that both lines, that the lines contain, right? So in this case, like 5, 0 is not on the line. So 5, 0 is not a solution. But 5, 4.5 looks like it is, or 5, 4.5 looks like it's a solution. And 5, 4.5, 4 2/3 would fall in that. All right, so if you have infinite solutions, your solution set's going to look like this. It's going to be a single ordered pair, but it's going to match up everything, or it's going to represent every point on the line. All right, so we have seen a system where I have intersection. We've seen a system where there's no intersection, where they're parallel, and then we've seen a system that is dependent because they're both the same line. Now, graphing is not always going to be available to us. So we have determined, or we've created some algebraic ways to determine what are the solutions to a system of equations. One of those methods is called substitution, the other is called elimination. For substitution, it's exactly what it sounds like. You take one equation and substitute it in for the other. Now, which one should you do? If one of your equations is already solved for one of the variables, you just take what's on one side. So if you get your variable, like in the system right here, in equation 1, I have 2/10 x is equal to 2y minus 15, and then right here I have x minus 2y equals 10. So I'm going to solve one of these equations for x or y, and then I'm going to substitute the result into the other equation. Now in this one, you can solve for x or y, but you typically want to do the one that's going to need the least amount of work. And surprisingly, to me, that looks like equation 2. So equation 2 is x minus 2y is equal to 10. I can get x by itself by just adding 2y to both sides. And now I have x is equal to 2y plus 10, or 10 plus 2y, both are the same things. Now, I'm going to substitute this into equation 1, because it's the one I didn't use. All right, so equation 1 is 2/10 x is equal to 2y minus 15. And what do I know? Well, I know x is equal to 2y plus 10. So that means 0.2. And then that x gets swapped out for the 2y plus 10. Right? And let me do this one in red here to really drive the point home. So there's 0.2x is equal. All right, so that's the left-hand side. The right-hand side stayed the same. On the left, we need to distribute 0.2 times 2. 2 times 2 is 4, and I get 1 decimal place. So that's 0.4y plus 2/10 times 10 is 2. Got linear equations, and now I have one equation and one variable. So take a look at the equation 2 when we started. Equation 1 and equation 2 both had an x and a y in it, right? If you've ever heard a math teacher say you got 2 equations, then you can get a solution, right? 1 equation, 1 solution, 2 equations, 2 solutions. If you have 2 equations, we can use this procedure here to solve one of them. If I just had 1 equation, and I'm saying it wrong. 2 equations, 2 unknowns. I have 2 equations, I have 2 variables. So that means I should be able to solve this. And what did I do? The substitution took my equation from having 2 variables to just having 1. And now that I only have 1 variable, all I gotta do is solve for y. So everything with the y to one side, everything else to the other. So the 0.4y is moving to the right. The minus 15 is being added, or the 15 is being added to both sides to get rid of the negative 15 on the right. So that goes to 0. 2 plus 15 is 17. And 2 minus 4/10 is 1.6y. Negative 15 plus 15 is 0. And then finish it off. I want y to completely by itself, so that needs to be divided by 1.6, which means I didn't leave myself enough room, which means that y is equal to 17 divided by 1.6 is 10.625. All right. And I'm okay with decimals. Here, it's not that big a deal. Now, that is only the y coordinate. Okay, so now I have to come back and I'm going to resubstitute this into, now I need to find x. All right, so I go back to my original. I'm going to pick equation 2, doesn't matter which one you choose. And equation 2 says x minus 2y is equal to 10. Well, I know what y is. Y is 10.625. And now I have one equation, one variable. X minus 10.625 times 2 is 21.25. And then get x totally by itself, plus 21.25 plus 21.25. We find x to be 31.25. So what is my solution? My solution is the ordered pair, or the point, 10.625, comma, 31.25, and that is contained in the solution set. All right. Now, look at the equations that are in the system. They're both linear, right? So if you have two lines, they only have three options. Either they're parallel and they never intersect, which means there's no solution. They're not parallel, but they are independent, which means they cross, but they can only cross once, right? A linear equation either rises or falls at the same rate forever. If it crosses once, the line that's on top can't curve back down and hit the one that's below it again. And the line on the bottom can't curve up to the top and hit the other one. So whenever you've got a system of linear equations, you're either going to end up with no solutions, one solution, or infinite solutions. All right. Now, if you plug that y value back into equation 1 instead of equation 2, you would end up with the same answer. All right. So that is substitution. Okay. Substitution is my favorite, and anytime, so this one wasn't, the equation 2 wasn't solved for any one variable, but if you ever get an equation, you get a system where one of the equations is literally y equals, and then all the terms in x, or x equals all the terms in y, substitution is going to be the way to go. All right. The other method of solving the system is called elimination. And for elimination, what we do is we take equations 1 and 2, and we're allowed to multiply them by any coefficient we want to, right? If I multiply the left and the right-hand side of an equation by 2 or 3 or 4, as long as I do it on both sides, it's still legal. Well, if I do that, I can multiply the equations by different numbers, and then I can either add or subtract the equations. And I want to multiply by certain numbers so that when I add or subtract my equations, one of them goes away. So let me show you what I mean. So I'm going to take equation 1 here, 2x plus y equals 5, and then I've got equation 2, negative 4x plus 6y equals 12. This 2x and this negative 4x, if I add those together right now, I'd end up with negative 2x. But if I can make this 2x into 4x, and then add the two lines, I would get 4x minus 4x is 0, and x would go away. So that's what I'm going to do. I'm going to multiply equation 1 by 2, which is going to lead to 4x plus 2y is equal to 10. It's important, you have to remember to multiply both sides. And then equation 2, I did not change. And now I'm going to add them. When you add two equations, 4x plus negative 4x is 0. 2y plus 6y is 8y. And 10 plus 12 is 22. the same thing happens as it did with substitution. One of the variables goes away, and now I'm left with a single variable equal to a constant or equal to some number, which I can solve. So y is equal to 22 over 8, which is 11 over 4. All right, and I'd say, well, let's just make that a decimal to make our lives easier. That is 2.75. Okay, so now I'm going to take that result. I'm going to plug it back into one of the originals. Which one? I'm going to do equation 1 because I don't have to multiply the 2.75 by 6. So equation 1 says 2x plus y is equal to 5. Well, I said y is 2.75. And now I'm going to solve for the variable that I don't know, which is x. So subtract 2.75 from both sides. And 5 minus 2.75 is 2.25. And then get x by itself by dividing both sides by 2. And x is equal to 1.125. Got ahead of myself, 1.125. So that means the solution for this system is the point 1.125, comma 2.7. Okay. This probably feels familiar. It may have been a while, but it probably does feel somewhat familiar. All right, so substitution and elimination. Both of them are valid, both of them work, and that's all that matters, right? Those are the only two ways. You can solve it graphically. The problem is, what if you don't have graphical representation? What if you don't have the technology? Then the algebra is here for you. So just a reminder of the properties that we talked about. A system can be consistent or inconsistent. And so what I want to do is I want you to take this system of equations here, and it's either, let's find out what are the solutions, and then let's see what are the properties that it carries. So equation 1 is 2x plus y is equal to 3. Equation 2 is 2x plus y is equal to 1. All right, well, they are not the same line, right? Because the left-hand sides are the same, but the right-hand sides are not. So what do I do here? Well, I can substitute, or I'm going to use elimination, right? I'm going to, because if I subtract equation 1 and equation 2, these x's will fall away, right? So if I subtract 2x plus y is equal to 3, a very large subtraction sign, and 2x plus y equals -1. If I subtract these, what happens? 2x minus 2x is 0, y minus y is 0, 3 minus -1 is 4, and we find out with something that is false. All right, so if all the variables fall away, your system is either, your system is either independent, or is either dependent or inconsistent. In one case, it has no solutions. In the other case, it has infinite solutions. If you end up with a false statement, that means if all the variables subtract away to numbers on what's this? A false statement means the system has no solutions, right? And I want you to think about what that means. Think about what is this math trying to tell me? It's trying to tell me that I can find a solution to the system 2x plus y equals 3 and 2x plus y is equal to -1 when 0 equals 4. When does 0 equal 4? Never. So when am I going to find a solution for this? Never. So my solution set is the empty set, which is represented by the 0 with a line through it. Okay? Do not put brackets. That is called the empty set. Leave it just like that. Putting brackets around it makes it a set containing the empty set, which is a big old mess. So if there's no solution, that means my system is inconsistent, but still independent because the lines are not the exact same line twice. All right. Now, speaking of dependent, independent, we have y equals x minus 1/3 and 3y equals 3x minus 1. In this one, I want to solve. So I have equation 1 and equation 2. Equation 1 is already solved for y. Look at that, right? Y is equal to x minus 1/3. So I'm going to take exactly what's in equation 1, and I'm going to plug this into equation 2 and see what I get. So equation 2 says 3y is equal to 3x minus 1. Well, from equation 1, I know that y can be rewritten as x minus 1/3. Distribute the 3x. 3 times -1/3 is -1, equals 3x minus 1. Now remember, the goal here is to solve for the variable, so that means I need to get the x's all on the same side. So I'm going to subtract 3x to move them all to the left. But what happens? 3x minus 3x is 0. 3x minus 3x is 0. So I end up with -1 is equal to -1. So I wanted you to see this done one time with substitution, one time with elimination. And now, what do I have? All the variables subtract away. You're left with a true statement. And the system has infinite solutions because the lines in the system are equal. They're the exact same line again and again. You already saw this equation earlier. You saw the system earlier when I did it, right? I think I just had y is equal to 3x minus 1 all divided by 3, but it's the same system. I get something back that's true, so my solution set contains the relationship x, comma, and then you solve one of the equations for y, substitute in x minus 1/3. Why do I hand it off like that? Because if you tell me what x is, I can tell you what y value works for, right? If you give me x is 0, I know y is 1/3. If x is 3, then y needs to be 3 minus 1/3. And all of those points are solutions. All right, questions? then let's do some practice. All right, so first, we're asking for all the solutions to the system if they exist, and then give all the properties of each system. So all the properties means listed as consistent or inconsistent, dependent or independent. All right, so equation 1 and equation 2 are here, and both of these equations, neither of them are already solved for one variable. So elimination or substitution, both are fine. If you wanted to do substitution here, a good value or good letter to use here, your variable would be x, because x does not have a coefficient, right? If I wanted to solve equation 1 for 3 for x or y, I would have to end up dividing by 3 or dividing by 4. If I wanted to solve equation 2 for y, I'd have to divide by -3. So I can do substitution, solving the second equation for x and plugging it in, or I can do elimination and multiply 1 or 2 by a number that will make one of the variables go away. Well, 3x and x, that's easy. If I can just multiply that by -3, I'm going to end up with what? -3x plus 9y is equal to -18. Equation 1 doesn't change. You are allowed to do this twice. You can do different. You multiply equation 1 and equation 2 by different numbers and then add them. For instance, if you wanted to get the y to fall out, you need to multiply the top one by 3, the bottom one by 4, and then add. Okay, so I have 3x minus 3x. I'm going to add these. And 3x minus 3x is nothing, so the x's go away. 4y plus 9y is 13y. And then 5 plus -18 is -13. For this system, please don't think this is correct, but don't fall into the trap of if the value of the x coordinate or the y coordinate is not a whole number, I must be wrong, because you just saw systems on the last page where they're decimals, and that's absolutely fine. So I found y is to be -1. If y is -1, I need to find x. So where am I going to go? I'm going to go back to my original, and I'm going to plug in 3x plus 4 times -1 is equal to 5. That's where that -1 comes in. And then just solve for x. -4 is equal to 5. Subtract 4 from both sides. 3x is equal to 9. Divide both sides by 3. X is 3. So my solution set contains the point 3, -1. And that system is consistent because it has at least one solution, and independent because the two lines are unique. All right, next. 3x minus y is equal to 2. 9x plus 3y is equal to 4. I'm going to, and you just, at the very beginning of this, once you figure out which method you're going to use, pick the variable you want to get rid of. So this is equation 1, this is equation 2. I want to get rid of y because that's going to be easier. Well, now let's get rid of y. Because if I multiply equation 1 by 3, I'm going to end up with 9x minus 3y is equal to 6. Equation 2 is exactly the same, plus 3y as it was, equals 4. And so my goal is to get rid of the 3, is to get rid of the y's. And that worked. -3y plus 3y is 0. But when I do that, 9x plus negative 9x is 0 also. So I end up with 0 equals 10. Well, you know already that if one of the variables, if both variables fall out, you either have a consistent and dependent system, or you have an inconsistent independent system. Which one is this? Well, I got something that's false. And if all the variables fall away and I get something that's false, that means there are no solutions to this system. Which means I have the empty set as my solution set, making the system inconsistent, but still independent because it's not the same line twice. All right, if you graph those two lines, what are you going to find? You're going to find out that these two lines are parallel, right? The left-hand sides are identical, the right-hand sides are different numbers. So all this is two lines that never touch or never cross because they're parallel. And then lastly, I've done elimination twice. Let's go back to substitution just to make sure we're good with it. In this one, equation one's already solved for x, right? So this is definitely going to be substitute. Equation one into equation two. Equation two says 2x plus 6y is equal to 10. But I know that in equation one, that x can be rewritten or is equal to 5 minus 3y. Everybody cool with that, right? That's what's happening there. If x is equal to 5 minus 3y, then I can replace that 2x with 2 times 5 minus 3y. And now I have one variable, and now I just need to solve. So distribute that 2. So 10 minus 6y plus 6y equals 10. Negative 6y plus 6y is 0. So 10 equals 10. This is true. So this means what? My system, what do I have? I have the same line twice. So my system is consistent but dependent, right? Consistent but dependent. Now, how do you write the solution set for that? Well, remember I said you have to get one of the equations and solve it for y. It's not done for us in this one. So I'm going to take equation one. I'm going to solve it for y. It's going to let me write my solution set. So solve for y means get first everything with y on one side, everything without on the other. X minus 5 is x minus 5. Negative 3y. I want y by itself, so I'm going to divide each term by negative 3. And what do I have now? Negative 1/3 x. Negative 5 divided by negative 3 comes out to 5/3. And then negative 3y divided by negative 3 is y. So that means my solution set contains what? X comma negative 1/3 x plus 5/3. And we are consistent because we have at least one solution, but we are dependent because I was writing depending, but dependent. All right. How do we feel about 8.1? All right, so 8.4, let's get it going. Now all we're doing is instead of having two linear equations, now we're going to have systems of nonlinear equations. So what do we see here? Equation 1 is y is equal to the square root of x. Equation 2 is y is equal to 1/3 x cubed. The first way to solve a system of equations, just like before, you can graph them and find their intersections. And that's exactly what we've done here with Desmos. So we know the solution set contains the 0.00 and the 1.552, comma 1.246. So how are you going to solve this? Well, graphically is done right there, right? Oh, sorry. Solve the system graphically. Well, this system down here is not the same system that's graphed up here. All right, so this is one way to do it, and this is the square root of x and the 1/3 x cubed. Now, let's change the system. So if I want to solve this system graphically, I'm going to do it the exact same way. I will take y is equal to the square root of x, and y is equal to 1/2 x squared. In Desmos or in the calculator, you can find the intersections. Desmos is a bit easier because if they intersect, you can find it and then highlight it. So I found it. So what do? I take a picture and then I put it in the graph. So that's how to solve that system graphically. Are they the same answers as the problem above? No, they're not, because they're a different system. So what does that look like? It looks like that. So my solution set all right, now that my equations are no longer linear, now my equations can curve, right? They can go up and down, which means I'm not limited to a single solution. So that means my solution sets are going to be more than just no solution, one solution, or infinite solutions. So the solution set contains 0, 0, and it contains 1.587, comma 1.26. Ordered pairs, and then notice they're separated by commas in the solution set. Now, how would you tackle this algebraically? Okay. Well, algebraically, what would I do? Well, treat it just like we did what we were doing before. This is equation 1, this is equation 2. Okay. Equation 1 is solved for y. So sub into the other equation. Yes, both of them are solved for y, so you could sub equation 2 into equation 1 or equation 1 into equation 2, whichever one you want. So equation 2 states that y is equal to 1/2 x squared. But equation 1 tells me that I can replace y with the square root of x. Is everybody comfortable with that? That's probably the toughest concept, is equation 1 allowed this to happen, right? Y is equal to the square root of x. Once the substitution is done, now it's algebra. This is old stuff now, right? I want to solve for x. That means I need to get x alone. This x is currently trapped under a square root. I've got to get it out of that square root before I can do anything else with it. So how do I get rid of a square root? I square it. If I square one side, I have to square the other to retain equality. So that means the square root of x squared is x. 1/2 x squared all squared. 1/2 times 1/2 is 1/4. And then x squared squared, raise the power to a power, and you multiply. All right. And now I have two different terms with x in it. Let's get them all to one side, which means subtract x. Subtract x. X minus x is 0. On the right, I cannot subtract this x from the x to the fourth because they're not like. So all I get to do is write 1/4 x to the fourth minus x. Well, now I have, on the right, I have two terms. Both of them have x in it. I want to solve for x. So I'm going to factor one of those x's out, and that's going to leave me 1/4 x cubed minus 1. Why is that? Why do I suddenly have like the bad guy face on the my plans are going exactly like I wanted to? Because I have two things multiplied that give me 0. Why is that important? Because by the zero product principle, if two things multiply to 0, then either the first is 0 or the second is 0. Right? That doesn't look or jump off the page quite like a polynomial broken down into two binomials works, because the first one is just a single monomial, the second one is a binomial. This is still the same process. Two things multiply to give me 0, one of them is 0. So x is 0, or solve this for x. Everything with an x is already on the right. So everything without an x needs to go to the other side. 1/4 x cubed. If I multiply both sides by 4, that clears my fractions. This is the same thing as dividing by 4. Multiplying both sides by 4. It'd be the same thing as dividing both sides by 1/4, which ends up being multiplying by the reciprocal. So what do I have now? 4 times 1 is 4, is equal to 4 times 1/4 is 1. So the coefficient is now just 1, which I don't have to write. So now I have 4 is equal to x cubed. I'm trying to solve for x. So if I want x by itself, it's currently cubed. I need to take a cube root. If I do that to both sides, I find that the x is equal to the cubed root of 4. So I have two possible solutions. X is 0, or x is the cubed root of 4. All right. Now, what are the solutions? All right, well, remember the next step. I found the values of x where these two lines intersect, right? And now I just need the ordered pair. I need the y coordinate for each of these. So for x is 0, equation 1 is y is equal to the square root of x, right? So that means y is equal to the square root of 0, which ends up as y is 0. Equation 2 says that y is equal to 1/2 x squared, yeah. So this y is 1/2 times 0 squared. 0 squared is 0, 1/2 times 0 is 0. These match, so that means 0, 0 is a solution to the system. Okay. What about my other equation, or my other answer? My answer here is the cubed root of 4. So y is equal to the square root of x. Well, x is the cubed root of 4. So now I'm taking the square root of a cubed root. This is where I'm just going to bring in some calculation and give myself a decimal answer here. So what is the cubed root of 4? 4 raised to the 1/3 power is 1.587. Okay, so let's equal to the square root of 1.587, and then what's the square root of that? 1.587. 1.26. All right, so that's it for equation 1. What about for equation 2? Equation 2 says y is equal to 1/2. And I'm going to go ahead and plug in for x of the 1.587 squared. I would put all of that in the calculator in one step, or all that into Desmos in one step. 1/2 times 1.587 squared. Did I get the same thing? Yes. They're not exactly the same. And the reason for that is the rounding, right? The fact that we rounded x to 3 decimal places and then plugged it in. But my y's match. So that means what? That means the point 1.587, 1.26 is also a solution. So the solution set contains 2 points, and they are 0, 0, and 1.587, 1.26. Close point, close the set. All right. That's going to start, that'll feel pretty normal as you're going through the system, as you're going through these equations now. You find out what the value of x is, plug it into both equations in the system, make sure both of them return the same number. And when they do, you've got a solution. All right. We're not going to go beyond 2 equations in a system. So you don't ever have to worry about running into a system that at least for this class, where you have 3. All right. So what about if I want to do this algebraically? Well, it turns out all the rules we learned for linear systems carry over to nonlinear systems. So I can still use elimination and I can still use substitution. So if I want to find all of the solutions to this system, how would I do it? Just like before, this is equation 1, this is equation 2, and take a look at that. Equation 2 is already solved for y, right? It's already solved for y in terms of x. So I'm going to sub this into equation 1. Equation 1 is a circle, right? So equation 1 states that x minus 5 squared plus y squared is equal to 25, but the substitution lets me replace y with 3 square root x minus 8. And that's all because equation 2 is already solved for y. So now I have one equation, one variable, and then I can just dive right into this. X minus 5 squared is x squared minus 10x plus 25. 3 squared is 9. The square root of x minus 8 times the square root of x minus 8 is x minus 8. And then the right-hand side's 25. X squared minus 10x plus 25. Distribute that 9. So it's going to be plus 9x minus 72 is equal to 25. This is quadratic, right? Highest power of x is 2. How do you solve quadratic equations? You get everything to the same side. So everything goes on one side. Let's combine like terms on the left before we do that. And what have I got here? 72 Negative 72 plus 25 is negative 47. Negative 10x plus 9x is negative x. So x squared minus 10x plus 25 plus 9x. So x squared minus x. 25 minus 72 is negative 47. So everything's combined correctly. And now I just need to get everything on the same side. So subtract 25 from both sides. And luckily, I just added 25. So to undo that, it takes me right back to where I was. X squared minus x minus 72. That's a quadratic, right? How do I solve quadratics? I break this down into two binomials. And there are two numbers that multiply to negative 72 and add to negative 1. So those numbers are negative 9 and positive 8. By that zero product principle, I know that x minus 9 is 0 or x plus 8 is 0, which means x is 9 or x is negative 8. All right. And then we take those and we check them. So come over here to the side and I'm going to check 9. The original equation, the easier one to deal with is equation 2. But remember, we have to do both. So for equation 1 says x minus 5 squared plus y squared is equal to 25. But I know that x is 9. So 9 minus 5 is 4. 4 squared is 16. Subtract 16 from both sides. Y squared is 9. Take square root of both sides. Y is positive and negative 3. Right? What about if I plug in x equals 9 to the second equation? Well, the second equation is y is equal to 3 times the square root of x minus 8. I'm plugging in here for x is 9. 9 minus 8 is 1. Square root of 1 is 1. 1 times 3 is 3. So what happened? This is why we have to do both equations, because my first equation indicates that when x is 9, you can get y, you can end up with a y as a positive 3 or a negative 3. For the second equation, I don't have the possibility of plugging in a negative 3. So if I plug in negative 3, I end up with imaginary answers. So this means that the only solution for y, the only value of y that works for us is positive 3. So all that match. And that makes up the point. We're plugging in 9, 3. All right, so my other point. The other point I had was negative 8. I'm going to check it over here. And if you see something right off the bat that you know is going to break it, go ahead and do it. For instance, equation 2 says y is equal to the q, or 3 times the square root of x minus 8. Well, if x is negative 8, negative 8 minus 8 more is negative 16. And the square root of negative 16 is 4i. Okay? No complex solutions. We're not interested in complex solutions in this section. So once you run into that, once one of your answers or once one of your possible answers causes you to end up with complex solutions, you know that that value of x, in this case -8, is not going to lead you to an answer. So that means, what's my solution? My solution set contains one point, and that point is 9, 3. So show me you can do it algebraically, and then you can see it right there in the notes. I don't have the picture in here, but you can see it. I've put this in Desmos already, and you see that equation 1 is a circle, equation 2 is a square root. So the square root rises slowly and it crosses the circle one time and it crosses at the point 9, 3. So use the graph to give your answer confidence, but don't use the graph to get the answer and not show any work on these. All right, so that is 8.1 done. Yeah, you're good. I'm gonna go ahead and stop. And then I've got 6 more problems. I'll do the rest of these and call it 8.4. And then I'll post that video before I leave my office today at 3. All right. So any other questions? All right, y'all do the same.